right, last section of chapter 1. We're going to continue talking about continuity like we did yesterday, but we're going to focus more on actual, more solidified things like trig functions and exponential functions. And of course, we'll also talk about inverse functions because that's what the title says. Right off the bat, we're given a nice little bit of information. If f of x is a trig function like sine, cosine, tangent, blah, 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 then as long as the limit exists, which it should, you could just plug in c and get your answer. Now there's going to be, and c of course is like if the limit is as x approaches pi, you can plug in c and you'll get your answer. There are times where maybe the answer is 0, like tan pi is 0. I believe, let me just double check. If you're concerned about like times that maybe it doesn't exist, like some of you might remember tan being like a weird, strange thing. If you were to plug in tan of pi over 2 into your calculator, it's going to tell you that it doesn't exist. And that gives us the answer already, that it doesn't exist. So you should be able to, in a calculator and algebraically, plug in the value for a trig term and get the answer that you're looking for. You don't have to worry about left side and right side matching up. You don't have to worry about discontinuity or anything along those lines, or maybe like a dot showing up way up there. No, just plug it in. So if I wanted to find a, according to the theorem that I have written up there, all I have to do is find out what cos 2 pi is, which I believe is 0, but let's just double check. Cos 2 pi. It's also very important that as you do these, you make sure that your mode in your calculator is set to radians. I was wrong. Cos 2 pi is 1. There you have it. Let's do a little bit of math over here. This is going to end up being sine 3 squared, which is 9, minus 3 minus 6 over 3 minus 3. Now, right off the bat, we might look at that and say, you can't do that because you get 0 over 0. Well, let's backtrack. You're right, we can't do that. But you know what we can do? We can remind ourselves that if I plug in a limit and I get 0 over 0, then what I can do is I can factor out the top, and if I have to, the bottom, and see if anything goes away, see if anything crosses out. If I factor out the top, remember you're looking for two numbers that add up to -1, multiply out to -6. Those two numbers are going to be x minus 3, x plus 2, sorry about the bad handwriting, over, what was that, x minus 3. That'll cross out. And so the limit as x approaches 3 of just sine x plus 2 is going to be the same thing as sine x plus 2 or sine 3 plus 2 or sine 5, which is just going to be some terrible, horrible number. Let's plug it in, see what it is anyway. Negative 0.9589. Okay, so lesson learned, plug it in, see what happens. In an instance like B, where you get 0 over 0, then you have some techniques that you learned in the previous lessons that you can use to simplify things and make your answer possible. Anything is possible with the Lord. Believe that. Do you recall inverses? Well, I do. And let's remember how to find inverses. The point of this is just to remember what those things actually are, what the inverses mean, and a little shortcut that we could use here or there to remember some of the basic or most important parts of what an inverse is. To find an inverse, you take the original problem, you swap the x and the y, so now it looks like that. You solve for the brand new y, so subtract both sides by 2. In this case, if I'm trying to get y all by itself, I'm going to square root both sides. Don't forget, when you square root both sides to solve for an equation, you have to include the plus or negative symbol. That gives us y equals plus or minus, positive or negative, the square root of x minus 2. And the last thing to top off what the inverse looks like is you're going to want to add that little inverse symbol right there. So the inverse of that guy is that guy. Let's remember how to graph the original problem. Okay, the original problem was x squared plus 2, so you start at 2. If you plug in 1, you get 3 over here, and you also get 3 over there. If you plug in 2, if I even have the space, I don't, it would go up to 8. So I'll just, no, I'm sorry, it'll go to 6. We're fine. My fault. And that'll go up like that. That'll go up like that. The domain and the range, the domain for the original problem goes all the way to the left and all the way to the right. Remember, the domain represents the x values in a function. If I were to, well, let me be careful, the x values in a relation. I'm getting my Algebra 1 vocabulary all screwy, and you'll see why in a minute, because this is a function. This one's not. But anyway, the domain are the x values. My x values, if this were to keep going, it'll continue going all the way to the left, and that'll continue going all the way to the right. So my domain is going to be negative infinity to infinity, or I can also use the phrase all real numbers. My range is going to be where I start from the y values to where I go from the y values. Well, if I start from the bottom, where Drake started, my range doesn't start until I hit 2. So my range happens at 2, not parentheses 2, but the bracket 2, because we include 2, and it goes all the way to positive infinity. That's my range. Now to graph this guy. If I were to plug in the x value of 0, I would get 0 minus 2. Square root of 0 minus 2 is nothing, so I can't do that. What if I plugged in 1? 1 minus 2 is, oh, that won't work either. Huh. What if I plug in 2? What if my x value is 2, and I do 2 minus 2 is 0? That's fine, and plus or negative 0 is positive or negative 2. So if I plug in 2, I get 2, 0 right there. If I plug in 3, I get 3 minus 2, which is 1, and my answer is going to be positive 1 and negative 1. If I plug in 4, I'm going to get 4 minus 2, square root of that sloppy. If I plug in 5, I get 5 minus 2, square root of that sloppy. If I plug in 6, I get 6 minus 2. Ooh, the square root of 6 minus 2 is the square root of 4, so I get positive or negative 2. Wait a minute. I think I see a connection here. First off, that is not a function like I previously mentioned. But let's find the domain. And let's find the range. I don't know. I said I see a connection, but I'm not sure if I'm right. I am right. My domain, let me see. Going from left to right, nothing, 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 nothing. Oh, magic happens at 2, and it seems to go on forever to the right. So it goes to infinity. Just like the range did. The range is, that line is going to just keep moving downward, and that line is going to keep moving upward. So this line continues going up forever and down forever. So my range is going to be from negative infinity to positive infinity. That is so incredibly weird that the domain and the range flip-flop. It's almost as if my x is my y and my y is my x. Do you see what I'm doing? If you remember inverses, the graphs of inverses are reflections over the line y equals x. Okay. Probably back in Algebra 1 or 8th grade math, you learned about reflections, and probably in geometry, you learned about reflections over the line y equals x. Well, this is a mirror image over that. Now, that's kind of hard to see, but if I move my graph like this, it seems like it's better. If green was my original problem and green was looking in the mirror, what you can expect to see back is blue, and that's what's going on. So literally what we have with inverses is inverses, if I give you y equals, inverse is a flip-flop of x and y values. What once was x is now y, and what was y is now x. And there you have it. That's what inverses mean. So that's going to kind of help us understand the graphs of some of the exponential functions that will look like in a little bit. Back in Algebra 2, you learned, maybe pre-calc, you learned what logarithmic functions are. You also learned a little bit more about exponential functions. Logarithmic functions are inverses of exponential functions. If I give you something like 2 to the x equals a number, and your job was to solve for x, like again, 2 to the x equals 84. That's just some random number. We would spend so much time trying to figure out what decimal x has to be so that 2 to the x equals 84. Or we could just learn logarithmic functions, which is an inverse of that. If you look at the graph below, you can kind of see what I mentioned in the last slide, where I have that, I like this little circle here. I have that mirror going on here, and this is a mirror action from one to the other. And if you tilt your head to the side, you can see it a whole lot better. That leads us to this. If x is continuous at each point on its domain, and its inverse is continuous on each point on its range, which is the f's domain, we have a little theorem. If b to the x is continuous left to right, then log b of x is continuous 0 to infinity. Okay, this guy is continuous and I'm looking at blue. I'm looking at 2 to the x, which is an example of b to the x. For all I care, this could be 3 to the x, e to the x, whatever. E, remember, is 2.71, blah, 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 blah. This is continuous going left to right, and it always will be. Its logarithmic function, in this case, log sub 2 or log sub 3 or log sub e, ln, is going to be continuous from 0 to infinity. Because that's its domain is this guy's range. Just a little theorem. Whether it pops up, I don't know. I don't remember. It's just something that we have to recognize due to the nature of inverses. Now, I don't know why I moved my face. Oh, I'm getting dizzy. Squeeze theorem. Oh, man, I could use a squeeze theorem from a friend, some of you are thinking, because of COVID-19 and you miss people. Same thing. It's not the same thing, but it's the same thing. Basically, the squeeze theorem says that if I just take something that's periodic, like a sine or a cosine or something along those lines, I could squeeze it so that it goes to the same point. What this means, and we can kind of see this, the opposite in action over here in this guy, but we do see it over here, is the problem with a thing like A is I can't plug in 0. That's no good. However, without needing to use, graphs, and without having to use, plugging in a really, really, really small number on the left side and a really, really, really small number on the right side to see if they go in opposite directions or if they go to the same thing. Squeeze theorem gives us two theorems that I can actually use. Sine x over x, I can't plug in 0, but I know, according to this picture over here, that the limit as x goes to 0 of sine x over x is 1. Okay, there's a hole there in reality. I can't plug in 0. So if I said, what's f of 0 of sine x over x, the answer is going to be, it doesn't exist. However, its limit does exist because the left side goes to it and the right side goes to it, and they both go to 1. Similarly, for the limit as x approaches 0 of 1 minus cos x over x, the left side goes to 0, the right side goes to 0, even though if I were to try to plug in 0, it wouldn't work. It's impossible. It can't happen. Okay, so squeeze theorem gives us these cute little things that will probably show up and come in handy in the next couple problems, which we're going to do right now. All right, so let's take a look at these three problems right here. Before I go too far, let's remind ourselves of what we learned in the last slide or the last page. The two rules that we were given thanks to the squeeze theorem. The limit as x approaches 0 of sine x over x equals 1. The limit as, let me move that cord out of the way, as x approaches 0 of 1 minus cos x over x equals 0. Okay, I'm going to make sure that I use these three things so I don't have to rely on, or these two things rather, so I don't have to rely on graphs. Did I forget to write out one here? I did. Silly me. And you can't even see what I'm doing. Oh, there you have it. Okay, so what can I do here? Well, what we're going to do with all of these is if we're not directly given these guys, we're going to turn these guys into one of these guys by either changing the trig function into what we need or moving stuff out, vice versa, yada, yada, yada. What I'm going to do first here is I have the limit as x approaches 0. I know what tan x is. I know that tangent is sine over sine. So tan x is sine x over cosine x. What I can't forget is that x is still living in the denominator, so I'm going to leave it there. To break this down more clearly, what I just did is I created a brand new fraction, and actually I created two new fractions. One fraction is sine x over x times 1 over cos x. The limit as x approaches 0 of sine x over x, according to that guy right there, is 1. So you become 1. Okay? The limit as x approaches 0 of 1 over cos x is cos 0, or 1 rather, over cos 0, and cos 0 is 1. So when you plug in 0 for x here, cos 0 becomes 1. So I get 1 times 1, which equals 1. So once you remind yourself what tangent actually means, it's pretty straightforward. This is not so straightforward, this next one. Okay? Not so straightforward at all. What I'm going to do before I try the problem is I'm going to rewrite this out. The limit as x approaches 0 of sine smiley face over smiley face is going to equal 1. I didn't change anything. I just turned x into smiley face. Well, why am I doing that here? Do I have sine x over x? No, I don't. But what I have is sine 4x over x. So this is what I'm going to do. I'm going to multiply the top and the bottom by 4 over 4. Now watch what I do. What that gives me is the limit as x approaches 0 of, I'll bring the 4 out front, 4 sine 4x over 4x. Now what we have here is I want you to make believe that instead of 4x, we had smiley face. So let's just pretend that this is smiley face and this is smiley face. I mean, they're the same thing, so why not just call them smiley faces? Well, according to this guy, the limit of sine smiley face over smiley face is 1. So the limit as x approaches 0 of 4 times sine smiley face over smiley face is going to be 4 times 1. This guy right here became 1 because the sine of x over x, or in our case, the sine of 4x over 4x, or in this case, the sine of smiley face over smiley face is 1. So I get 4 times 1 over here, which is 4. Tricky, 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 tricky. You may have learned back in pre-calculus a trig identity that looks like this, and I'm going to remind you of this before I even attempt C. Sine squared, and this comes from the Pythagorean theorem, sine squared x plus cos squared x equals 1. Well, do I know what sine squared x is over x? No, that doesn't really help me here. I'm kind of in trouble. Although, do I need to do this way? I'm looking at this now and I'm thinking I don't need to do it this way. There's probably 2 ways that I can do this, but I'm sticking with what I'm doing. If sine squared x plus cos squared x equals 1, I could solve this for sine squared x by moving that cos squared x over there. So sine squared x is the same as 1 minus cos squared x. So what I'm going to do is I'm going to rewrite this out and turn this, I don't know why I put a parentheses there, into 1 minus cos squared x over 2x. Remember difference of squares? Difference of squares says that if I have a square minus a square, or in this case 1 is 1 squared, minus cos squared x, which is cos times cos, I could split it up into 1 minus cos, 1 plus cos. That's what I did. And looky there. According to this guy, as my limit approaches 0 of 1 minus cos x over x becomes 0. So what's going to happen is I'm going to end up with 0 times 1 plus cos 0, who cares what that is, over 2, because whatever that is just going to become 0 anyway, because I'm going to multiply everything by 0, and my answer is 0. Now, my other option that I was thinking, and maybe I'll quick write this out, and hopefully this works out. There's another way that I can do this. I mean, I just saw the cos squared. I got excited because I love my trig identities. I guess another way that I could have done this is I could have said the limit as x approaches 0 of sine x times sine x. Remember, cos squared x is sine x times sine x over 2 times x. Right? And what we learned from up here is that sine x over x is 1. So this part right here, this chunk right here just becomes 1, so times 1. Sine 0 is 0. So when I plug in my limit, I get sine 0 over 2, which just becomes 0 anyway. Just look at that. Just fun. Oh, I can't imagine a more fun way of ending the chapter. I can't. I literally can't. I'm sitting here racking my brain, and I can't think of a more fun way to wrap up chapter 1 than all these trig identities. If you don't remember your trig identities, then YouTube trig identities, and you'll get to see some videos, I'm sure. But that's the end of chapter 1. I had fun. I hope you did too. Onward to chapter 2 and derivatives. Bye!